This exercise has several parts. We're going to take them one at a time. First, estimate the partial sum S sub 10 of the series the sum as n goes from 1 to infinity of 1 over n to the fourth, and estimate the error. There's not any way to do the first part except to plow through it. And we're talking 1 over 1 to the fourth plus 1 over 2 to the fourth plus 1 over 3 to the fourth, so on, all the way up to 1 over 10 to the fourth. Calculator value, 1.08203658, and I'll stop it there. As far as the error, it's not always clear, but for this, we're asking to estimate the remainder. R sub 10 is, according to an inequality we wrote in an earlier video, less than or equal to the integral from 10 to infinity of 1 over x to the fourth dx. Well, that means that R sub 10 is less than or equal to the limit as t approaches infinity, because we do have an improper integral, from 10 to t of 1 over x to the fourth dx, which, using the power rule, gives us the limit as t approaches infinity of negative 1 over 3x cubed evaluated from 10 to t. And this is going to equal 0.000333, and they go on forever. So R sub 10 is less than or equal to that value. For the next part, we're asked to use the inequality S sub n plus the integral from n plus 1 to infinity of f of x dx is less than or equal to s, which is less than or equal to s sub n plus the integral from n to infinity of f of x dx, that pink and the blue integral that we saw in a previous video. Anyway, we're going to use that to get a better estimate of the sum. What this means for us, since we use s sub 10, is that the sum s is between s sub 10 plus the integral from 11 to infinity, that's the n plus 1, of 1 over x to the fourth dx, and s sub 10 plus the integral from 10 to infinity of, I almost wrote f of x, 1 over x to the fourth dx. Well, we know what s sub 10 is. That's our 1.08203658. The integral from 10 to infinity we just computed. That's our 0.000333. So the sum of those two numbers that I just said form the upper bound for the sum of the series. And the integral from 11 to infinity is computed in exactly the same way as the integral we just saw using the power rule. And you can confirm that has a value of about 0.0002504. So that added to 1.08203658 formed the lower bound for the sum of the series. We can then say that S is between 1.08228698 and 1.08236988. Notice that these two values both start with 1.082. So we at least have that degree of accuracy for the sum from adding up 10 terms in the series. Part C asks us to compare this with a known value. The sum as n goes from 1 to infinity of 1 over x to the fourth was actually computed by Leonhard Euler, and he found that it was equal to pi to the fourth over 90. I'm sure he just guessed it and just happened to be right. Sure, that's how things work. Putting that into calculator would give us approximately 1.082323233. That's as much as I'm going to write. But notice that we had the 1.082 already. The rest of it is just more accuracy. And finally, part D asks us to look at this from a slightly different lens. Find n so that S sub n is 0.00001 of the sum. That is, how many terms do you need to use if you know you need to be accurate to within 5 decimal places? So we want actually R sub n to be less than or equal to 0.00001. Well, based on the inequalities that we have, we know that that means that we want the integral from n to infinity of 1 over x to the fourth dx to be less than or equal to 0.00001. And this is weird because the unknown is actually a limit of integration, but the integral should be fine. We're going to use the power rule. It's the same integral that we already saw. We're looking at the limit as t approaches infinity of the integral from n to infinity of 1 over x to the fourth dx, which is equal to the limit as as t approaches infinity of negative 1 over 3x cubed evaluated from n to infinity, which is going to have a value of 1 over 3n cubed. Well, we want that 1 over 3n cubed to be less than or equal to 1 over 10 to the fifth, I'll call it, which means that 10 to the fifth should be less than or equal to 3n cubed by finding reciprocals of both sides. And then isolating n cubed, we get n cubed is greater than or equal to 10 to the fifth over 3. By taking cube roots, we get that n is approximately 32.18, but we needed n to be at least the number that we just got, and n has to be a whole number. We're not talking 32.18. Therefore, we can say that n has to be at least 33.